So my today's topic is conditional probability and not conditional probability. My today's topic is Bayes theorem, and I shall be discussing three problems today, which are very important. And if you understand these problems, you'll be able to understand the logic behind how to apply Bayes theorem in problems, and what are the differences of Bayes theorem with conditional probabilities, etc., etc. So you be very attentive, because I'm not going to do the calculations. I'm going to show you the presentation, so you need to be very attentive so that you understand. And if you have any doubt, you can unmute yourself and you can ask me anytime. Okay, so let's begin. I shall start with the definition of Bayes theorem. It's where you can see I have considered a circle. This circle is denoted by A, and this A is nothing but an event. Now, I have considered only one event, and it has a subset, or you can call it as a sub-event, and that is capital B, which is the shaded circle, which is lying inside capital A. Now this is my case. Okay, now under this, with respect to this diagram, if I say that capital A be any event and capital B be any sub-event of A, then Bayes theorem states that if you are supposed to find the probability of the event A, given that the event B has already happened, is nothing but probability of B given that A has happened into probability of A by probability of B. Why conditional probability is important here? You see, to get this result, where my cursor is moving, to get this result, first of all, I have written probability of A slash B in the form probability of A intersection B by probability of B. And you know very well from my previous class that this is the formula for conditional probability. And in the numerator, probability of A intersection B is there, which has been again broken into two halves. One is probability of B slash A, and another half is probability of A. So there also I have applied the definition of conditional probability. So that's how Bayes theorem are interconnected with conditional probability. Okay, I have used the definition of conditional probability twice while I writing the formula for probability of A slash B, and while breaking the formula of probability of A intersection B. Now, if capital A and capital B are independent events, then Bayes theorem doesn't have any meaning, because in that particular case, probability of A intersection B will be simply PA, and PBs will cancel each other. So Bayes theorem only holds when the events are not independent. Okay, and you see another important thing is that on the left hand side of the equation, probability of A given B is there. Means you are supposed to find probability of the event A given that the sub event has already happened. This probability can be found with the help of just the opposite. That means probability of the sub event given that the original event has already happened. So therefore, since these two poles are connected via a formula, therefore Bayes theorem is sometimes known as theorem of inverse probability. Okay, or Bayes theorem problems are known as inverse theory problems. Okay, so that is the formula for Bayes theorem when only one mother event and one baby event is there. Now we shall generalize the structure of Bayes theorem in case 2. Okay, what is that structure? Structure is, we shall now consider two mother events like this. Let capital A and capital B be any two events. Now, one thing you see, I have mentioned here that capital A and capital B are two mutually disjoint events. And not only that, they are exhaustive events. What do we mean by that? Okay, when you read something, you have to understand the meaning of each word present in the sentence. So I shall try to clarify these points to you. But I shall not talk about mutually disjointness right now. I have a case 3 for Bayes theorem. When I shall move on to case 3, then that particular part will be clarified to you. Not right now. It is not possible to clarify this particular point because there are only two events. You will automatically understand by yourself. Let me talk about exhaustive events. Why am I saying that capital N, B and capital A and capital B are exhaustive events is because if we combine them, means if we take the union of capital A and capital B, then we get the total sample space. Okay, that means in the sample space is consisting of only these two events, no other extra events are present. Okay, so we have exhausted all the possibilities. We have considered all the possibilities or possible events over here. So that's why capital A and capital B has been taken into consideration. They are exhaustive events because capital A and capital B, their union is the total sample space. Now see the diagram. In the diagram, capital A has a sub-event, which is the shaded region denoted by capital U, and capital B is has another sub-event denoted by the shaded region, which is named as capital B. Let me save the chat. People are coming and writing their roll numbers. Otherwise, I will forget later. So, so capital A has a sub-event capital U and capital B has a sub-event capital B. Now, if we combine these two sub-events, U and V, by union, then let us name this event as capital C. So capital C is the union of the two sub-events. So obviously, since capital U is a sub-event of capital A, capital B is a sub-event of capital B. So obviously, their union, capital C, will be sub-event of the union of the two sets, capital A and capital B. So I have written over here that C is the sub-event of A union B. If we are now supposed to find the probability of the event A, given that the event C, that event C has already happened, then by the definition of conditional probability, I can write it as probability of A intersection C divided by PC. And in the numerator, since probability of A intersection C is there, we can again break it into two halves. By the definition of conditional probability, we can write it as probability of C given A into probability of A. But in the denominator, you see, I have written something else. Previously, in the denominator, probability of B was only there. Now, I have not written it as probability C only. Probability of C has two possibilities. One possibility that C is dependent on A, another is C is dependent on B. So I have broken it into two halves again. So I have written in the denominator that probability of C can be written as probability of C has happened, the probability of C given that probability of A has happened into probability of A plus probability of C is given that probability event B has happened into probability of B. Because C is a sub-event of A union B and not only A and not only B. So this is a further generalization of case one, and that is another structure of Bayes theorem. Now you can ask me one question at this juncture. Can I write probability of B given C in this way? Obviously, you can do so. There will be only one change in the numerator. In the numerator, you will write probability of B intersection C instead of probability of A intersection C. But the denominator will remain same. Numerator will change. So that can also be written. Okay. So that is one type of generalization where two mother events are there and one baby event, that is capital C. Let us further generalize this structure of Bayes theorem. Now we have considered small n number of events denoted by E1, E2, En. And n is mutually disjoint. These n events are mutually disjoint and exhaustive events, and so and so. Let us go to the picture. And now I'm going to make you understand what do we mean by this word mutually disjoint. Try to recall. When you learn probability, first of all, you came across two terms. One is mutually exclusive and another is disjoint. But you know very well that mutually exclusive and disjoint, they are synonymous to one another. Here neither I have mentioned mutually exclusive nor I have mentioned disjoint. Rather, I combined them together and I wrote mutually disjoint. What do you mean by that? Is it a printing mistake? No. It has a meaning. What is that meaning? The meaning is, see, I have drawn several circles over here. Several circle means several events. You choose any two events pairwise. is let it be capital E1 and capital En. Then capital E1 and capital En are mutually exclusive. Let us choose E3 and EJ pairwise. They are mutually exclusive. Let us choose EI and EI plus 1, mutually exclusive. Let us choose EJ and E100, mutually exclusive. Let us choose E1 lakh and E1 crore, mutually exclusive. So you take any pair, they are mutually exclusive. So therefore, they are known as mutually disjoint. Okay. Now we have considered mutually disjoint events, and they are exhaustive because in the sense which has already been clarified to you, that if we combine these events E1, E2, E3, E4, En together, then their combination is the total sample space. So E1 to E3, En, they are mutually disjoint as well as they are exhaustive. Now each event has sub-events. Okay, S1 is the sub-event of E1, S2 is the sub-event of E2, S3 is the sub-event of E3, and so on. Sn is the sub-event of En. If we combine these sub-events together by union, if we write S1 union, S2 union, S3 union dot 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 union Sn, then let us name this sub-event as capital A. Now we are going back to our statement of the Bayes theorem, okay, which is a generalized version of the previous statements. We have considered n mutually disjoint events, which are also exhaustive, and let capital B be any sub-event of union I goes from 1 to n ei, means capital A is the sub-event of E1 union E2 union dot 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 union En, total sample space. Then if I am supposed to find the probability, the conditional probability of event Ei, given that sub-event A has happened, it can be written as, see the numerator. I have written just the opposite, probability of the event A given that the event Ei has happened into probability of Ei, and in the denominator I have written the same expression preceded by a summation sign, where summation runs from I goes from 1 to up to n. That means here you are considering probability of A given E1 into probability of E1 plus probability of A given E2 into probability of E2 plus dot 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 probability of A given En into probability of En. And this result is true for all I. Means if you are going to put I equals to 1 in the numerator, in place of I you are going to put 1, denominator will remain unchanged. If you are going to substitute I equals to 2 in the left hand side, in the numerator also you are going to substitute I equals to 2, denominator will remain unchanged. If you are going to substitute I equals to n on the left hand side, in the numerator also you are going to do the same thing, denominator will remain unchanged. So that is the generalized version of the Bayes theorem. Okay, so these are the three versions of Bayes theorem which I have discussed right now. Let me save the chat once more. People are writing the roll numbers. Okay. Now we are in a safe side. Now let us go to our first problem. Our first problem, you see this girl? Many girls are today attending my classes. You see, suppose you are one, this girl is one of you. Okay, and you are so busy in writing the examination, and your parents have told that you shouldn't miss a single question. You have to write all the questions. Okay, and that is a verdict. So you are so much afraid, and you are just what should I say? You are just thinking that what will happen if I do not know all the answers. Some answers are definitely known to me because we are good girls, but some other answers are not known. So we have to guess it. Okay, just like you guessed in my pre-test examination. Okay, some people guessed and some people knew the answer. I don't know who guessed and who knew the answer. Oh, so this is the condition of the girl which is shown in the picture. What is the question? Question is, suppose that when answering a question on a multiple choice test, a student either knows the answer or guesses at it. If he guesses at the answer, he will be correct with probability 1 by 4. If the probability that the student knows the answer is 0.6. Now, what is the conditional probability that the student knew the answer given that he answered it correctly? Now you see, often it is not explained from where these values 1 by 4 and zero point 0.6 come from. Okay, we just start solving the calculation without thinking much about the source of these information. Now you see, think about your pretest which you gave in the introductory session. Before the introductory session, in the pretest there were 4 alternatives. Okay, and suppose a particular student doesn't know the answer, didn't know the answer, so he will select the alternative. If he is not getting help from his friends, if he is by if he is on his own, then he will try to guess it, and in that particular case the selection of each alternative will be equally likely. So he is going to select the alternatives with probability 1 by 4 because four choices were there. So that's how I got the probability 1 by 4. If the probability that student knows the answer 0.6, what does it mean? Many students are attending my today's class who are from different boards. Some are from CBSE board, some are from ICSE board, and some are from state boards, West Bengal board or Bihar board. Now, probabilities are probably there in class 12 or class 10. Probably they have come across probability before, but they forgot. Okay, now it may so happen that students, the probability chapter was there but teacher didn't teach it, or student missed it intentionally. Many things may happen. Okay, and maybe for some boards probability chapter was not even there. So I'm guessing probably 60% students knew the answer. Probably, I'm not sure about it. That's why it is written 0.6. So this is the basis, this is the source from which you are getting this information 1 by 4 and 0.6. Now I have been asked, you took the examination, what is the conditional probability that the student knew the answer given that he answered it correctly? Always remember, in this type of problems, you have to write the events properly. You have to count the events properly. You have to judge how many events are there, and you have to name it properly. If you do not do so, then you will not be able to solve the problem correctly. So be very careful and attentive, and let us see how to define these points of these events before we start applying Bayes theorem. Because application of Bayes theorem, there is nothing significant in applying Bayes theorem, but naming events, identifying the total number of events present, that is very significant. So I am naming events in this way, that let K be the event where student knows the answer. Let capital G be the event where student guesses the answer. And let capital C be the event that the answer is correct. Now, once the events are defined, I am going to put the information given in the problem in mathematical sense. Okay, so what is given in the question? It is given that when the student guesses at the answer, then he will be correct with probability 1 by 4. Read this statement very carefully, which is equivalent to probability of C given that G, and which is equal to 1 by 4. Also, it is given that probability that he knows the answer correctly is 0.6. See the naming of the events. So this probability is nothing but probability of K, Pk. So these information are given in the question. We are supposed to find the conditional probability that the student knew the answer, that is probability of K, given that the answer is correct, slash capital C. So probability of K by C is supposed to be found out. Let us apply Bayes theorem. By applying Bayes theorem, I can write probability of K slash C as, first of all, let us apply the definition of conditional probability. So it can be written as probability of K intersection C by probability of C. Now let us apply Bayes theorem. Probability of K intersection C can be broken into two halves. Write the reverse, probability of C slash K into probability of K by probability of C. We need to find the probability of C first of all. Then only we can find the remaining portion of the problem. What is probability of C? Probability of C is what is the probability that the answer is correct. Now the answer can be correct in two ways. Student knew the answer and it is correct, or student guesses the answer and it is correct. So I have broken this into two halves. Let me read it out for you. First half is probability that the answer is correct given that student knew the answer into probability that student knew the answer, plus probability that the answer is correct given that student guesses the answer into probability that student probability of guessing the answer. Now you see, when the probability that the answer will be correct given that student knew the answer, it is certain event, and since it is a certain event, its probability is 1. Probability that student knew the answer as it is given in the problem, it is 0.6, so I have written here 0.6. Probability that student the answer is correct given that student guesses the answer is given to be 1/4 in the problem, so it is 1/4. And probability that he guessed the answer, either student knew the answer or he guessed the answer. So these two events, K and G, they are complementary to one another. Since K is given to be 0.6, so obviously G will be 0.4. So I have written here 0.4. Okay, so all the values that have been substituted in the expression, and it I have calculated it as 0.70. So PC is obtained. Let us substitute in the formula of Bayes theorem. Probability of K by C thus becomes, you see, probability of C by K, probability that student answer is correct, student knew the answer, it is 1. Probability of student knew the answer, it is 0.6. And the probability of C, which you have calculated, is 0.7. So ultimately you are getting 0.85714. 85% chance approximately that all the student knew the answer given that the answer was correct. That's why I told you you are very good students, and because 85% chance that you answered it correctly by knowing it. Okay, so thus we apply Bayes theorem in this particular problem. Now my next topic is, have you read, the question is, have you read the Michael Williams story? I'm not going to discuss in details the story of Michael Williams. So if you have not read, you just read it after the class ends. What did Michael Williams say? What was the story in brief? In the story was, she was very ill and some monitor was attached to her bed, hospital bed. A monitor started beeping after a regular interval of time. Nurse avoided it and thought it to be a false alarm. And after 25 minutes, when nurse attended, and she saw the condition of Michaela deteriorated, and after 15 days she died. Now alarm beeped, but it was a false alarm. Now look into the chart. That was the story in brief. Look into the chart. There are two types of conditions in reality. One is called predicted condition, another is called true condition. And for each of these conditions, there are two possibilities, positive and negative, positive and negative. Now, if your predicted condition and your true condition are same, then that is called true positive. If your predicted condition is negative and true condition is positive, then it is called false negative. If your predicted condition is negative and your true condition is negative, it is called true negative. And if your predicted condition is positive and your true condition is negative, it is called false positive. I have highlighted all these four conditions are very important, but I have highlighted false positive because my Michael Williams story is based upon false positivity. Not only this, nowadays we are facing the problem of COVID-19. Suppose I start coughing at home and my neighbors thinks that his predicted condition is Shobik has got COVID-19 and he informed police. Okay, I have got a COVID-19 patient in my neighborhood. Police comes and takes my blood sample and makes me quarantined and tests me. And suppose my tests results in negative. My neighbor's predicted condition was positive and actual condition is negative. So I am actually false positive. My condition is false positive. So, so very what should I say? Is very critical condition is that it's very not possible to cough in public place. If you, even if you don't have you do not have acquired COVID-19. Now the question is, next problem is, a blood test is 99% effective in detecting a certain disease when disease is present. Okay. However, the test yields also a false positive result for 2% of healthy patients tested. That is, if a healthy patient is tested, then with probability 0.02, the test will say that this person has the disease. Suppose 0.5% of the population has the disease. Find the conditional probability that a randomly tested individual actually has the disease given that his or her test result is positive. Okay, the question is in front of you. You keep on reading the question. Let me start solving it. Let capital D denote the event that the person has the disease, and let capital E be the event that the test is positive. Read the question. We are supposed to find the conditional probability that a randomly tested individual has the disease, probability of D, given that his or her test result is positive, slash E. Now, by definition of conditional probability, probability of D slash E is equal to probability of D intersection E by probability of E. And then by Bayes theorem, I can write it as probability of E slash D into probability of D by probability of E. Same old thing. Our job is to find probability of E, isn't it? Our job is to find probability of E. Now, I have broken this into two halves. Probability of E has been written as probability of E given that test result is positive, given that disease was there, into probability of the disease, plus probability that test result is positive, given that disease was not actually there, and probability that disease was not there. So you see, all the information are given in the problem. Probability of E slash D is nothing but 99%. So I've written here 0.99. Probability of having the disease is 0.5%. So it is 0.005. Probability of E given D bar, it is what? 0.02. This information is given over here. You see, I'm marking the point. And probability of V bar is just a complementary event of D. V bar is the complementary event of D, so it is 0.995. That's how probability of E has been calculated. Substitute all the values together in the expression and you get 20%. Thus, there is approximately a 20% chance that a randomly chosen person from the population who tests positive actually has the disease. I have a question for you at this point. Think and tell me later on, okay, why this percentage is poor, why it is not high, it is not higher than 60%, why it is so poor, so low. Okay, probability that the person has the disease, given that the test result is positive, why this percentage is so poor? So you keep on thinking about this. Okay, so the answer is 20%. My last problem of today's class is this one. Oh my god, a funny picture is there. What the problem says? Problem says the inspector in charge of a criminal investigation is 60%. Is 60% certain? Is 60% certain of the guilt of a certain suspect? A new piece of evidence proving that the criminal was left-handed has just been discovered. Okay, so he's carrying the pistol in the left hand. Whereas the inspector knows that 18% of the population is left-hander. He is waiting, Amitabh Bachchan is one of them. He is waiting to find out whether the suspect is left-handed. What is the probability that the suspect is left-handed? Amitabh Bachchan can also be the suspect. If the suspect turns out to be left-handed, what is the probability that the suspect is guilty? Okay, our job is to name the events first of all. Our job is to name the events first of all. So what are the events? There are two events. One is capital G, that the suspect is guilty. Another is capital L, that the suspect is left-hander. Person is left-hander. Probability of G. Probability of G means suspect is guilty. Okay, so this percentage is 60% as it is shown in the question. So it is 0.6. Probability that the suspect is left-handed, given that it is not guilty, he is not guilty, it's 0.8, because 18% of the population is left-handed, and until unless it is proved, no one is guilty. So it is 0.18. Sorry, it is 0.18. We are supposed to find probability that the suspect is guilty, given that he is left-handed. That is to find. First of all, we are supposed to find probability of L, because why? Why is it so? because probability of G by L is written given by the conditional probability formula as probability of G intersection L by probability of L. Now, again, I have broken it into two halves by applying the Bayes theorem problem, which is probability of L given G into probability of G by probability of L. Now, how to calculate probability of L? That is the most important part in Bayes theorem problem. Finding the denominator is one of the most important parts after naming the events in Bayes theorem problems. Probability of L means what is the probability that suspect is left-handed? There are two possibilities. Suspect is left-handed given that he is guilty. Suspect is left-handed given that he is not guilty. Suspect is left-handed given that he is guilty. This is certain event and it is one. Why is it certain event? Read the question once again. The investigator has already found out the suspect is left-handed after postmortem the body. Okay, so it has become the certain event because of the postmortem report, and so it is one. Probability of G is zero point 0.6. You already know it is given in the problem. Probability of L given G bar is 0.18 given in the question, and G bar is the complementary event to G. So probability of G bar is 0.4. So you put all the values, calculate, it is 0.672. Now you substitute all the values together here, and the result comes out to be 0.8928. If I have not done any mistake in calculating, so you check the calculations by yourself. You'll be getting this note published in Google Classroom by today evening after the class. Now I have shown you three problems of Bayes theorem. I have given one problem as a practice problem to you. This problem has been selected from the exercise of John Pune books, which I shared with you. What is the problem? An explosion at a construction site could have occurred as the result of static electricity, malfunctioning of equipment, carelessness, or sabotage. Interviews with construction and engineers analyzing the risks involved led to the estimates that such an explosion would occur with probability 0.25 as a result of static electricity, 0.20 as a result of malfunctioning of equipment, 0.40 as a result of carelessness, 0.75 as a result of sabotage. It is also felt that the prior probabilities of the four causes of the explosion are 0.20, 0.40, 0.25, 0.15. Based on all these information, you are supposed to find two things. One is what is the probability, what is the most likely cause of the explosion, and what is the least likely cause of the explosion. Answers are given to you. Most likely cause is sabotage, probability is given to you. Least likely cause is static electricity, the answer is also given to you. You are just supposed to recalculate the problem by yourself and verify with the given result. Okay, so in today's class we have discussed this much for today. In today's class we have discussed how to apply Bayes theorem in problems and why Bayes theorem is related to conditional probability and not independent events. I'm again repeating, if the events are independent, there is no meaning in calculating Bayes theorem. Bayes theorem collapses for independent events. Bayes theorem only stands high when the event is not. Yeah, Aman Kumar Chaudhary raised his hand. You want to say something? You can unmute yourself. I'm already done with my class. Aman raised his hand. You want to say something, Aman?
No,
Okay.
sir.
Okay. Thank you. Acha. Okay. So if you have any doubt, you can write in the chat, or you can WhatsApp me, or you can write in the Google Classroom. Whatever. Probably you have understood what I mean to say. Remember this important point, you can note it down, that Bayes theorem, under what condition Bayes theorem collapses? That is one important question. Bayes theorem collapses when the events are independent. Very important uh, point. So, so this much for today. I hope you have understood today's today's topic. Okay, you uh, collect the problems from the exercise of John Freund and start doing the problems on conditional probability and Bayes theorem as much as you can. Tomorrow we are going to meet at the scheduled hour in the evening at 3:20 probably, and we'll be continuing with our further topics of the syllabus. So till then, see you soon and bye, and stay safe, stay healthy. Okay, so if you have any doubt, you can tell me. Otherwise, I'm going to disconnect. I have saved your chat. Right now, I'm saving your chat. So, do you want to say anything? Okay, thank you so much.
Thank you, sir.
Okay, okay.
Thank you, sir.
Yeah,
Bye.
yeah, yeah.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.